This program was produced by the Chemical Heritage Foundation. Our mission is to collect, preserve, and make known the history of chemistry, chemical engineering, and related sciences and technologies.
The semiconductor technology has been the key to modern electronics. It's changed the way the world works. This is all because this powerful technology has allowed us to make more and more complex and high-performing circuits. They're the basis of everything electronic we have. Unprecedented in anything in human history. They were the key product to make computers relatively ubiquitous. Places that were completely isolated previously now are connected to the rest of the world. And of course, it's a technology that has enabled all of these internet applications that consume people today.
This is the story of the man behind this revolution. He's a chemist, visionary technologist, accidental entrepreneur, self-made billionaire, and philanthropist for the world. His childhood passion for chemistry led him to the path that forever changed the world we live in.
I'm Gordon Moore. I've spent most of my career in the semiconductor industry. From the beginning, when silicon transistors were a rarity, to the point now where they're ubiquitous, I've enjoyed every minute of it. My first interest in chemistry was developed when my neighbor got a chemistry set, and I found some of the interesting things you could do with it. I decided right then I wanted to be a chemist, although I didn't quite know what one did. In those days, you get some really neat chemicals on a chemistry set. You know, potassium chlorate, for example, which mixed with a lot of things makes some pretty neat explosives. I eventually built a home laboratory which was significantly more elaborate, and I proceeded to make explosives on a small production basis. My standard yield of nitroglycerin was about 63 cc's, as I recall, which I turned into dynamite, for which I had to make mercury fulminate to detonate the dynamite. In those days, you could buy almost anything. You know, I would order all the chemicals I wanted. They'd be delivered to me by freight. I could even order things like picric acid, which is the equivalent of TNT. All you have to do is dry it out and detonate it. And I did. I ordered them and dried it out and detonated it.
Gordon's love of chemistry carried him through his studies at Sequoia High School, San Jose State University, and right on through to the University of California at Berkeley, where he earned a degree in chemistry. He then went on to obtain a doctorate in chemistry at Caltech.
I can't help but think how different the world is than when I graduated from here some 50 years ago. Then there were no computers on campus. In fact, there are only a few in the entire world. Can you imagine, though? No email, no internet. That's the life we had when we were here. In fact, for most of our calculations, we used an archaic device called a slide rule. How many of you have heard of a slide rule? Oh, okay. I see the history classes in here are still alive and well. I couldn't find a good technical job in California, so I had to go east for my first job out of school.
Upon graduation from Caltech, Gordon and his wife Betty moved east to Maryland, where he took a research position in the Applied Physics Lab of Johns Hopkins University, which was the Navy's proximity fuse and missile laboratory.
The U.S. Navy knew that it needed a better way to shoot down attacking planes, a problem that Axis scientists were also trying to solve. The breakthrough, one of the biggest of the war, and one that would turn the tide of the entire conflict, was the variable timing, or VT fuse. This technological innovation came from the scientists and engineers of the newly formed Johns Hopkins University Applied Physics Laboratory.
Gordon enjoyed his experiments, but in the end, he didn't find it rewarding enough. He wanted his work to result in something practical and useful.
And one evening, I got a phone call, picked up the receiver, and the voice on the other end said, "This is Shockley."
Gordon recognized the voice of William Shockley, the brilliant Bell Labs physicist who had co-invented the transistor in 1947.
It has been my experience that everything, all of the more difficult inventions I've made, and I counted recently and I find I have some 85 issued patents, which makes me at least close to being in the major league on numbers. Most of these require many failures to accomplish. One must, it's my own experience that to do creative work, one must overextend oneself, one must count on falling on his face.
Shockley told Gordon that he'd left Bell Labs and started an advanced transistor laboratory in Mountain View, California, in the area where both Shockley and Gordon had grown up. Shockley's lab was part of Beckman Instruments, a company started by a former Caltech chemistry professor, Arnold O. Beckman. Beckman had pioneered the pH meter, and his company was a leader in electronic instruments and computers. Shockley was in the midst of amassing a team of brilliant specialists and wanted Gordon to be the chemist on his team.
The kind of thing he was proposing to do was interesting. It was a brand new field. There wasn't much known in it at the time. I accepted the offer he made. It got me a job in Palo Alto, within 10 miles of where I grew up in Redwood City.
Gordon was happy to be back in the San Francisco Bay Area and to be part of an emerging new industry.
The electronics industry, particularly the semiconductor electronics industry, really is a chemical processing industry to a considerable extent. When I got into it, much of the chemistry wasn't understood and a lot of the techniques had not yet been developed. So it was really an open field.
William Shockley proved to be a difficult manager, ultra-competitive and distrustful. These difficulties and objections to the technical direction of the lab led Moore and a group of 7 other colleagues to leave Shockley and launch their own transistor company nearby. With backing from technology buff Sherman Fairchild, the founder of several aviation and defense companies, and the largest single shareholder of IBM, Moore and his colleagues started their new firm, Fairchild Semiconductor.
That was when we became entrepreneurs. For completely negative reasons, we set up what turned out to be one of the seminal companies in the development of Silicon Valley. That's why I considered myself an accidental entrepreneur.
Fairchild brought out the first NPN Silicon Mesa double diffuse transistor, the first PNP Silicon Mesa double diffuse transistor.
At Fairchild, Gordon and his colleagues helped create a new era of digital technologies that revolutionized the way the world worked. Their most important contribution was the creation of an integrated circuit, commonly known as the microchip, or simply the chip. A microchip is a thin slice of silicon with many transistors chemically printed into it to create an entire electrical circuit. Today, microchips have millions of transistors all interconnected to perform some useful function. Their work at Fairchild fueled the evolution of a remarkable location for technology, Silicon Valley.
I was probably more directly involved in the creation of what we call Silicon Valley than I'd like to have been. We were, first of all, an example. We broke off from Shockley and set up Fairchild, which was not something that was done commonly prior to that. But after that happened, Fairchild turned out to be the mother company of many Fairchildren, several dozen, and I wouldn't be surprised if it went in the hundreds of companies can trace their formation back to Fairchild and its spin-offs. So we became the beginning of this phenomenon where a few engineers would run off with a new idea, find backing of venture capital, which really developed out here at about the same time, and set up a new company to exploit the new technology.
In 1965, Gordon was invited to write an article for Electronics magazine, predicting what would happen over the next 10 years in electronics technology. He was inspired by what he was experiencing at Fairchild Semiconductor, especially the ongoing development of microchips. Gordon predicted that with improvements in the chemical printing process for manufacturing microchips, electronics would become far cheaper. More complex microchips would actually make electronics less expensive. He foresaw that complexity would dramatically rise to achieve these low costs.
And I looked at that, and it had almost doubled every year. A little noise in the curve. So I said, okay, in the next 10 years, it's going to continue to double every year. We're going to go from 60 components on a chip to 60,000 components on a chip. Pretty wild extrapolation. I wanted to get across, here's an idea where the technology is going to evolve rapidly and it's going to have a major impact on the cost of electronics. That was the main point I was trying to get across, that this was going to be the path to low-cost electronics.
Gordon predicted that to achieve low-cost electronics, the number of transistors placed on a chip would double every year.
Looking back from 1975, the 10 years, we may not have gotten 10 doublings, but we certainly got 9. So it'd been a reasonably good projection, and one of my colleagues dubbed this Moore's Law. I don't know exactly when.
In his article, Gordon saw that such great numbers of inexpensive transistors would change and spread the use of electronics. In doing so, he accurately imagined much of the now familiar world of modern electronics.
Because it only made sense if there were applications that could consume these large volumes of low-cost electronics. So I had to talk about home computers, phased array radar, electronic watches, and a variety of other things that at the time didn't really exist.
Moore's Law has become the guiding principle for the semiconductor industry, steadily improving the manufacturing process, delivering ever more powerful microchips, and dramatically reducing the cost of digital electronics.
Now, the nice thing about Moore's Law is it gets quoted in almost everything that grows exponentially. I've gone on to say that if Al Gore invented the internet, I invented the exponential. It's amazing how often I run across a reference to Moore's Law. In fact, I Googled Moore's Law and I Googled Murphy's Law, and Moore beats Murphy by at least 2-1. It's hard to pick out any single thing I'm most proud of. Perhaps the founding of Intel was my biggest success.
Although the environment at Fairchild was a major improvement over working for Shockley, Moore and his fellow Fairchild co-founder Robert Noyce grew concerned about the direction of the company, and together they chose to strike out on their own, again. In 1968, Gordon and Noyce decided to spin off a new semiconductor company, which they called Intel. Noyce prompted the pair's departure, but it was Gordon who devised the business and technology strategy for Intel. In 1971, Intel introduced the first commercial microprocessor, the brains of a whole computer on a single microchip. Since, Intel has been the industry leader in producing ever more powerful microprocessors.
It's been a phenomenal evolution of a technology. By making things smaller, everything gets better. The electronics get faster, they get much cheaper, the power consumption could go down, and the complexity of the systems that are possible goes up dramatically, as does the reliability.
The chemical printing technology for making microchips has also expanded into a variety of other fields, such as DNA sequencing. It has proven to be one of the most powerful technologies ever developed.
E.O. Wilson, the biologist at Harvard, had estimated the number of ants on Earth as something between 10 to the 16th and 10 to the 17th. 10 to the 16th is a lot of transistors and a lot of ants, but we've kept growing beyond that. The printing press, how many characters get printed in all the newspapers, magazines, books that are published a year? I tried to estimate that and found that was comparable to the number of transistors we were making. Well, I think the technology of shrinking things is going to run out of gas here one of these days. That's not the end of progress. You know, we're already putting literally billions of transistors on a single chip. Billions with a B. That's a huge amount of capability. And those can be connected to form a vast array of different electronic functions. So I think electronics will continue to find its way into every nook and cranny of our existence. Well, chemists look at the world by what it's composed of. They look at the structure of the materials. They look at how to synthesize existing materials and new things that nature never thought of.
But what kept you going? What was the thing that kept you interested?
I kept learning more and more. It's exciting to learn new things. I guess that's really what it was. And then you get to do experiments, you get to learn things nobody else knows by doing research. That's a pretty powerful thing to have. You know, I'm the only guy in the world that understands this tonight. Tomorrow morning I'll publish it.